Hello everyone, welcome to Deterministic Optimization. My name is Andy Sun. I'm assistant professor in the Storr School of Industrial and Systems Engineering. From this week on, for the next 8 weeks, I'm going to be your instructor. From this week on, we're going to start a new unit called Linear Optimization. For this module today, we're going to talk about linear optimization modeling for a very important class of optimization problems called network flow problems. The learning objective of this lesson are the following. First, we're going to construct linear programming models for a wide range of applications. And we're also going to solve LP models with CVX, which is one of the very useful software that we're going to use for this course. And the third one is to recognize non-linear problems that can be modeled as linear programs. And this lesson, we're going to start from the first item here. So we're going to go over again ingredients of a linear optimization model, because I think in the first part of this class, you have already seen linear optimization models. And then we'll see a simple example to illustrate many aspects of the linear programming problems that we're going to cover in detail in this part of the course. Okay, let's look at ingredients of a linear program. First, a linear program, sometimes we also call linear optimization model, in exchange or in the same way, is composed of, first we need variables. So usually we write variables x in a boldface letter as a vector of n components. So you can see here that x as a vector has x1, x2, up to xn components. So n is called the dimension of the problem, meaning how many dimensions of variables we have. And another important aspect of a linear program is the linear objective function. So how do we write a linear objective function? A linear objective function f of x from x1 to xn is written as a sum of ci and xi summing over I from 1 to n. So this, you can also think about this as a weighted sum of the variables xi by a weight ci. And we call ci's the coefficient of the linear objective function. We can also write this as an inner product of the two vectors. One is the c vector, which has all the components of c1 up to cn. And x is the decision variable of components from x1 to xn. So all linear function can be written as an inner product of two vectors. Okay, this is a linear objective function, which arguably is the most simple objective functions that we can see in an optimization problem. All right, the next very important aspect of a linear program is, of course, the constraints. And for linear programming problems, we'll need linear constraints. And the linear constraints come in three different orientations, we can say. First, they share all the common feature, meaning all the left-hand side of the linear constraints need to be linear functions in the variables. So if you can see on the left, for example, the first one here, this constraint is a linear function of x from x1 up to xn. And it's a linear function, so it should have coefficient here because this is the first constraint. So we call this A1, constraint 1, of coefficient corresponding to x1. So A11, A12 up to A1n. It's not necessarily the case that all the A1s need to be non-zero. So maybe some of them are 0. That is fine. And then we have the so-called right-hand side, which should be a constant. So here is B1 is a constant. And then these two parts are linked by an inequality in the middle. In this case, it's less than or equal to. We can also have greater than or equal to as a linear inequality, or we can have linear equality, which is equal to. So all three types of linear constraints are allowed. We can also write them in a more compact form using inner product following the form in the objective function. So for the first constraint, the A vector, A1, is composed of this n coefficients for each of the variable xi, and we do need to have every one of the coefficients present in this vector, meaning this vector is a vector of n components. So this is a very compact way to write A1 transpose X less than or equal to B1, or A2 transpose X greater than or equal to B2, or A3 transpose X equal to B3. So a linear program is composed of variables and the linear objective function, which can be written as an inner product of a coefficient and the variable, and then a bunch of linear constraints, either in less than or equal to form, or greater than or equal to form, or equal to form. And the important thing is, in a linear program, we always want a finite number of such linear constraints. So here we have 3. It's okay to have 3,000, but it's not okay to have an infinite number of linear constraints. And later we'll talk about why that's the case. So let's go through a simple example of linear program. Here is a simple example of only 2 variables. The linear objective is to minimize x1 minus x2, subject to 2 constraints and also non-negativity constraints. So the first constraint is x1 plus x2 less than or equal to 2. This is a linear constraint because we have a linear function on the left-hand side and a constant on the right-hand side. And then the second constraint is x1 minus 2x2 greater than or equal to negative 2. And then we have another 2 constraint. I called it non-negativity constraint, which means it's imposing non-negativity on the variables. So x1 is greater than or equal to 0, and x2 is greater than or equal to 0. These 2 constraints are also linear constraints. I can also write the same linear program in the vector form. For example, the objective function here can be written as an inner product between the variable and the coefficient, where the coefficient is 1 and negative 1, which correspond to the first coefficient for x1 and the second coefficient for x2, which is negative 1. I can do the same for all the constraints. For example, x1 plus x2 less than or equal to 2 can be written as a vector 1 and 1 inner product with x1 and x2. I can do the same for all of them. And usually, we don't write x1 greater than or equal to 0 and x2 greater than or equal to 0 as an inner product. We can do that, but because this is such a simple constraint and is a bound on the variables, so we sort of treat them in a different way. So I can also write the constraint in the matrix form. So I can put the coefficient of the first constraint here as x1's coefficient and x2's coefficient. And then for the second row, I'm going to write the coefficients of the second constraint. So this is a matrix. And of course, I have matrix times vector, which is my variable. And then that usually we call is A matrix. And you see that here, on the left-hand side, I'm going to have 2 and negative 2. And of course, to be consistent with the constraints, I need to be sort of very explicit here to have less than equal to or greater than equal to. Later we'll see that we can always reformulate any linear program so that the sign or the direction of the constraint is always identical. So in that way, I don't have to write this for each different constraint, different orientation of the direction of the constraint. So the next point that we want to illustrate is to visualize the feasible region of this linear program. The feasible region means all the set of points that satisfy the set of constraints that we have. So here is a plot. Because we have only two variables, x1, x2 is on a plane, so we can actually draw this feasible region. So the way to draw the feasible region is we draw for each constraint. For example, x1 plus x2 less than or equal to 2 correspond to this line and everything below this line. How do you know that? Because we can first look at x1 plus x2 equal to 2, which is exactly this line. And then for the less than or equal to, that should contain the origin point, 0. Therefore, it should be the so-called half space of the entire half part of the space plus this line. So that's the first constraint, feasible region. And then the second constraint, we can do the same. It's x1 minus 2x2 greater than or equal to negative 2, which is this line here. That's the equality line. And everything below it, again, 0 is contained. So that's the second constraint. The third and fourth constraints are easy because these are just non-negativity. Means x1 is greater than or equal to 0. That, again, is this half space containing this line and everything to the right. And x2 greater than or equal to 0 is this line here, horizontal line, and everything above it. So what is the feasible region? Well, the feasible region is the intersection of all the constraints, these four constraints, which will give us this polygon area. We call this a polyhedron, P denoted. So that is the feasible region of this problem. We can also draw the objective function. Well, the objective function x1 minus x2 is this direction, meaning this direction is the direction vector of 1 and negative 1. And how do we find the optimal solution here? Well, the optimal solution is to minimize this x1 minus x2. How to do that? We want to push this back as far as possible until we cannot do that. So if you do that process, you see that the optimal solution should be here in the red dot. That is the minimum of this optimization problem. And optimal solution will be 0 and 1. All right, let's summarize this lesson. First, we learned how to construct a linear programming problem. And to construct a linear programming problem, we need to define variables, objective function, and constraints. Both objective function and constraints should be linear functions of the variable. And the objective function must be linear function, and the constraint must be linear equality or inequality constraints. Both are fine, but they have to be linear function. And we studied a simple LP in 2 dimensions. And we see that such LPs can be drawn in pictures, and also we can find the optimal solution geometrically on the picture.